Hello everybody. For this video, we're going to talk about section 4.2, which is focusing on the addition and subtraction formulas for the three basic trig functions, which is sine, cosine, and tangent. There are equivalent versions of these for the other three trig functions, but they are uh, a lot more rare in terms of usage and in terms of application. Um, there's a time for and place for these, but for this particular video, we are going to focus on the addition and subtraction formula for sine, cosine, and tangent. Here we go. Uh, these are the formulas for the three addition and subtraction formula. Sometimes I will refer to these as the sum and difference formulas. Of course, they are really the same. It just depends on which one is easier to say at the moment. So there is a little bit of pattern here. We are going to focus more on the sine and cosine here. The tangent one follows a very similar pattern, but is a little bit more challenging to derive that directly. In fact, all these books, all these formulas are justified using a geometric argument involving the distance formula, which I think the book does a decent job in explaining. So if you are interested in doing so, taking a look at the justification, we can see that from the book. For this video, we're just gonna go ahead and take this formula for granted, right, and take it as is, as a given, um, so we can use this formula for free. Anyways, when you're looking at this kind of formula, focusing on the sine formula first, and we can see that the sine functions, the sine addition and subtraction formula can have the addition sign corresponding to the addition sign, right? And then subtraction with the subtraction. Whereas for cosine, it's really the flip, right? Cosine of x plus y actually, give us a minus at the outside, and subtraction, right, cosine of x minus y gives it as a addition on the outside. So it's kind of flipped for cosine, but then stays the same for sine. That's one of the pattern. And the other pattern is if you take a look at the sine functions, right, the sine formulas, it's always alternating between the angles. So sine of x plus y, we get sine of x cosine of y, and then you flip that around to get cosine of x sine of y. Similarly, for the subtraction version, sine of x cosine of y, cosine of x sine of y. Basically, just remember that there is a alteration of the signs and then alteration of the functions involved with the different type of the difference in angles. On the other hand, for cosine, notice how it's always going to be cosine and cosine, and then sine and sine. Well, this way guarantees that you don't have to worry about which one we choose as x and y, because they always show up in pairs anyways, right? For cosine and sine, uh, like that. The subtraction one is very similar, except for, well, again, it changes sign from the inside to the outside, right? So inside is subtraction, the outside actually becomes addition. But then the terms are always cosine, cosine, sine, and sine. Okay, so these patterns is something that we are going to leverage to um, allow us to solve a certain type of problems. The first really application for this is to increase the type of values that we can solve using our basic trigonometry and unit circle. Now, this is something that takes some getting used to, but then once we do, we can start looking for angles that are not necessarily on the unit circle exactly. For example, we want to find the exact value of the following. Whenever we're dealing with exact values, right, you should always just think about not using the calculator. The calculator rarely gives us the good set of exact values. So ignore the calculator for these. most of these applications is there, so we don't need the calculator. Okay, so find the exact value of the following. Now, the angle 105 degree is not on the unit circle. What we can do here is to break this up into some sort of addition or subtraction. Okay, fairly easy to make this into addition because we have some fairly familiar angles that add up to 105, which is 45 plus 60. Okay, and now I have an addition of angles of cosine, so I can use the addition formula for cosine. And again, it's this one here. So it basically comes down to cosine of 45 degree, cosine of 60 degree, minus, remember changing the sign from the inside to the outside, sine of 45 degree, and then sine of 60 degree. Okay, so I'm just applying the formula up there. And again, for cosine, it doesn't really matter which one comes first. Um, you know, which one you choose as your x and which one you choose as your y. Doesn't really matter, as long as you stay consistent in terms of plugins, your formula is always going to carry most of these problems for you. The only thing left to do here is to actually evaluate these, but these are fairly easy to do. Cosine of 45 degree is radical 2 over 2. Cosine of 60 degree is 1/2. Minus sine of 45 is also radical 2 over 2. And then sine of 60 is radical 3 over 2. Okay, and then when you simplify this, you get radical 2 minus radical 6 over 4. And that is your final answer here. Okay, moving on to the next example. Here we're doing sine of pi over 12. Now the pi over 12 might be a little bit intimidating because again, fractions, right? We have to work with angles in a unit circle in terms of radians, and we need to combine them together to become pi over 12, which is a little bit difficult at first, but because we have common denominators, right, we can turn all of the common um, angles on the unit circle into denominator of 12, and you actually realize that this is really not too bad to do because in between any of the common angles, the gap, where the distance is pi over 12. So this pi over 12 is really just pi over 4 minus pi over 6. Okay, if you try to add these together, you realize you're gonna get 2 pi over 24, right? When you make common denominators, which come out to be pi over 12. And this is not the only choice. You can also do pi over 3 minus pi over 4, right? Again, any one of these common angles, the gap in between is going to be pi over 12. So here we have a subtraction formula for sine, and that's just using this formula right here. Okay, again, be consistent with your plugins, right? So here I have pi over 4 first minus pi over 6. So when I'm plugging that in, I have to kind of, keep my angles aligned with the correct formula. So this is equal to sine of pi over 4 cosine of pi over 6 minus, right, for the sine function, the sine on the inside and the outside is the same thing, both minus in this case. And then cosine of pi over 4 sine of pi over 6. Okay, so just double check with the formula, and I just have to plug in the rest from the unit circle. So sine of pi over 4, we know this is radical 2 over 2. Cosine of pi over 6 is radical 3 over 2, minus cosine of pi over 4 is radical 2 over 2, and sine of pi over 6 is 1/2. And when I combine these together, very similar to the last problem, we actually just gonna get radical 6 minus radical 2 all over 4. It is a very similar looking answer as before, but it just that's how the formula comes out to be, and this is the final answer for this problem. Now, in general, how do we deal with radian of denominator 12? Basically, we leverage this relationship, right? The pi over 12 and pi over 12 is equal to pi over 4 minus pi over 6. Where again, if you want to, you can go ahead and do pi over 3 minus pi over 4. Both this one is going to come out in a more straightforward way. That's okay too. But the way you want to leverage that is, for example, 7 pi over 12. You will simply write this as 7 times pi over 12. And we have a difference for the pi over 12, right? We can do this as 7 times pi over 4 minus pi over 6. And then we distribute the 7, so this becomes 7 pi over 4 minus 7 pi over 6. Okay? And those two angles are angles that we can work with on the unit circle. So you can basically handle all radian measurements with a denominator 12 like this. The only thing extra you might have to deal with is, say, if your angle is a little too big. Let's say if your angle comes out to be 11 pi over 4, then of course you have to then find a coterminal angle, right, that is within the 0 to 2 pi range. Okay, the next example is really the opposite of what we just did, right? Again, find the exact value of the expression. Now here, the angles in radians are a little bit more complicated, but we see that we have cosine, right? Two different cosines of different angles. Here's one, call it x, and here's another one, call it y, right? Plus, it's the same pattern for sine, x and y, right? Same trig expression, but for different angles. So what this does is it reminds me of the cosine formula. In fact, because I have an addition here, right, I'm reminded of this formula right here, this version right there. So again, the double cosine, right, plus the double sine. Okay, that means I'm really working with the difference formula for cosine. So what I can do is I can simply rewrite this entire equation as cosine of 17 pi over 18 minus pi over 9. And I can add fractions, so this becomes cosine of 17 pi over 18, making common denominator, multiply top and bottom by 2, 2 pi over 18. And this is going to come out to be cosine of, well, I guess 17 pi minus 2 pi is 15 pi over 18. And then I can simplify top and bottom divided by 3, looks like. So cosine of 5 pi over 6. And again, we have our trusty unit circle. So cosine of 5 pi over 6 is going to be radical 3 over 2. But because it's in the second quadrant, we need to put a negative. So this is our answer. Okay. Not bad of a problem. In fact, as complicated as this kind of problem looks, is very, should I say, choreographed, right? You can kind of see exactly where you're supposed to go from here because it's really obvious that you have to somehow combine the angles together, and the pattern for which the trig function shows up and the pattern, of the expression tells you exactly which one of these formulas we should be using. So there's really nothing scary about this kind of question once you identify, once you've seen it once, right? Once you identify what type of steps that you have to take. Okay, so you probably is can guess this is gonna show up eventually, and I guess better late than never, right? Or actually, this is not too late. This is already pretty early into the section. Anyways, this is going to be a interaction between trig and inverse trig functions. Okay, but as always, we're going to start off with a numerical expression. So over here we have two givens really. We got sine sine theta equals to 7/11, right? With theta in quadrant 2. Okay, so that's one part of the given. And the other one is that cotangent of, this is Greek letter phi, this is equal to 8/3, with secant of phi is less than 0, which is negative, right? This is really the same thing that we're working for in our section 3.4 and 2.5, except for now we have to do multiple triangles in the same problem. Okay? By the way, this letter is the letter phi. Okay, we're gonna just use the two Greek letters theta and phi for the angles in this particular problem type. Okay, so using this first part of the given, sine theta equals to 7/11, I can construct one triangle, label it theta, and sine is opposite over hypotenuse. And then the adjacent is easy enough to get by using the Pythagorean theorem, which is going to give me 11 squared minus 7 squared. Let's write this down. We have 11 squared equals to 7 squared plus 8 squared. And then 11 squared is 121, 7 squared is 49. And if I subtract 49 on both sides, I will have 72 equals to a squared. And when I take the square root of both sides, I just get radical 72 for a. Again, you really don't have to rationalize the denominator here, for later part of the problem. So just go ahead and leave it as radical 72. Similarly, we have the same setup for the cotangent of phi. Cotangent of phi, this is equal to 8/3, and construct my other triangle here. Phi. Cotangent is adjacent over opposite, so adjacent is 8, opposite is 3, and we can probably do this directly here. So this is going to be the hypotenuse is going to be square root of a squared plus 3 squared, right? A squared is 64, 3 squared is 9, so add that together is 73. Okay, I trust you can do this at this moment in time. The last thing I need here is to identify the quadrant. So here, according to all students take calculus, right? The first part, we don't need to do it because we're already given. Here, uh, theta is in quadrant 2. Okay? But for phi, we need to identify it, right? And we can do that by saying, hey, look, cotangent is positive. Well, cotangent is positive only in quadrant 1 and quadrant 3. And then on top of that, secant is negative. Secant is negative in quadrant 2 and quadrant 3. So that means my phi is in quadrant 3. Okay? So it's the only quadrant where cotangent is positive, but secant is negative. All right. Once I identify all this information, the only thing left for me to do is to go ahead and evaluate my expression, right? Again, this is my in-game goal here. So cosine of theta plus phi, this is equal to, by my addition formula for cosine, this is cosine of theta, cosine of phi, minus sine of theta, and then sine of phi. Okay, this is where we are going to leverage my triangles. You do have to be careful which triangle you're using, right? The angle tells you which triangle you're using. So cosine of theta, I have to use this triangle. Cosine of phi, I'm using that triangle. Okay, so be careful. This is exactly why you have to label your triangles so you're not making this mistake when you're writing down your answers. Okay, we went through all this work. You don't want to just have it messed up because you didn't label your triangle. Anyways, so we have cosine of theta, right? Again, we're using this side of my triangle. Cosine is adjacent over hypotenuse, so radical 72 over 11. And then cosine of phi, we have to use this triangle. And again, cosine is adjacent over hypotenuse, so 8 over radical 73. And then we play the same game for the sine. So sine theta, right? Again, because I'm using theta, I'm using the triangle on the left. So sine is 7 over 11. And sine of phi is going to be 3 over radical 73. Okay, and there's really not much to do here. If you want, you can simplify this a little bit. Just gonna move up that to the left a little bit more here. But it's really not much you can simplify because uh, this term comes out to be just very simply 8 radical 72 over 11 radical 73. I guess I can put that all together because I do have the same denominator. So 8 radical 72 minus 7 times 3 is 21, all over on the bottom 11 radical 73. Okay, that's my final answer. And again, this is a exact answer, so definitely no decimals. But see, this right here makes it super difficult to guess, right? If you're thinking, oh, I can just plug this into the calculator, get some answers, and then um, guess the quote unquote exact solution, right? Like maybe you can do that with radical 3 over 2, for example. But there's really no good way to guess this complicated of an answer. So what I've shown you here is the best way of tackling this kind of problem. Okay, going into the next example, this is where we are working with the inverse trig expression. And this is, again, a problem type that we've been doing for a couple of sections now. And the domain here, for any real number x, and then for y between -1 and 1, that is only to satisfy this expression of the tangent inverse in this case, which has domain all real numbers, and then the cosecant inverse function, which has domain -infinity to 1, -infinity to -1, union 1 to positive infinity. But then because I have 1 over y here, y has to be somewhere in between -1 and 1. The point here is that the restriction here is only there to satisfy the condition of my inverse trig function. It's not going to affect how you are going to do the problem. Okay? Basically, you can just ignore that. That's just a condition to make the problem make sense in theory. This is going to work out the same way as we've done it before, but again, do it with a little bit more steps. Okay, the question here is just as before, rewrite this complicated looking expression as a expression involving x and y only, or another way of saying this is a expression without using trigonometric or inverse trigonometric functions. Okay, here we go. I'm only copying down the question just so I can work with it a little bit better. You do not have to copy down the question. Okay, so what we're going to do here is just kind of like before, we're going to take my inverse function and let that be inverse tangent and let that be theta. And then now I have to kind of use a different letter here, right? Inverse cosecant function becomes my phi. And just as before, I'm constructing my triangle, but here I have to do two triangles, right? So tangent inverse x over 3, that's equal to theta. This by definition means x over 3 equals to tangent of theta. And from here, it's easy enough to construct my triangle. Label your theta. Tangent is opposite over adjacent. From here, the Pythagorean theorem gives me the hypotenuse is going to equal to x squared plus 9, right, which is 3 squared. Okay, square root of x squared plus 9. Similarly, I play the same game with phi. So we have cosecant inverse of 1 over y equals to phi. And then here, by definition, 1 over y equals to cosecant of phi. Drawing these award-winning triangles. Label your triangles. And cosecant is hypotenuse over opposite. That means the adjacent side, again, by Pythagorean theorem, is hypotenuse squared, so 1 minus opposite squared, so y squared. Okay, square root of 1 minus y squared. Now that I have both of these set up, just like before, this question becomes simply cosine of theta plus phi. Which means by my addition formula for cosine, this becomes cosine of phi, cosine of theta cosine of phi minus, because I have to be a different sign than the one on the inside, minus sine of theta times sine of phi. So now the only thing I need to do here is to rewrite these expressions, right, using the appropriate triangle. So for cosine of theta, I'm using the triangle on the left, and cosine is adjacent over hypotenuse. It's going to give me 3 over radical x squared plus 9. Cosine of phi uses the triangle on the right. Again, adjacent over hypotenuse. So 1 over 1 radical 1 minus y squared over 1. Now subtract. Sine of theta uses the triangle on the left again. So opposite over hypotenuse. X over radical x squared plus 9. And sine of phi uses the triangle on the right. Opposite over hypotenuse, which is y over 1. Okay. The last thing here is simplifying the expression, which is really very easy to do because there's not much cancellation happening. On the top, we just have 3 times square root of 1 minus y squared minus x times y all over, while the denominator is just the square root of x squared plus 9 times 1, which obviously is just the square root of x squared plus 9. And that is the final answer for this problem. As you can see, the result of this answer is very complicated looking expression, but if you perform this the same way as I'm doing, if you follow all of the steps here, it's really not too bad to kind of work this problem out. And the best part about this, I think, is there's almost no calculations here, right? There's no calculations here. It's just a bunch of rewrite, a bunch of different expression. And if you follow the steps here, there's really not that much room for error. It's gonna, make the problem overly difficult. Okay. Now, this is the last thing we're gonna do, and it's part of why this particular section is extra important, even though it's not the longest section that uses the, various identities. This one is rewriting the expression, right? Rewriting expression of the form a sine of x plus b cosine of x into an expression of the form k times sine of x plus phi. So we're basically combining two trig function expressions into one single trig function expressions. And it turns out there's a lot of application purposes for a problem like this, right? Mainly because it's very difficult to solve for this equation. We actually see this example at the very beginning of the class where we did sine x plus cosine x equals to 1, and we can only guess a couple of good values without able to, solve for those values. But if we can rewrite these two expressions into a single trig expression, then it makes solutions a lot easier to work with. That's the goal behind this task here, okay? So again, it's another rewrite expression, but this one is kind of unique because this one is turning two trig equations into a single trig expression, whereas the previous problem type that we're used to seeing in 2.5, 3.4, and of course now, we are rewriting this just to get rid of the trigonometry altogether, right? Again, there's no trig in here whatsoever. So this particular problem is somewhat unique. The development of this is fairly simple, right? If I want to get from here to there, uh, what do I need to basically what do I need to find? Well, we start from the, I guess, from the ending part. So starting from k sine of x plus phi, and we can apply the addition formula for sine to expand that out. Well, that is supposed to equal to this. So essentially, we're kind of going backward here, right? Just to retrace our steps, so to speak, and to find out how the functions are relating to each other. But as soon as I write out the equation, I can see that there's a pretty obvious relationship between the ones on the top and the one, basically the one on the top, this equation, and then the one expression on the bottom, because I have, if I imagine distributing the k into both of these terms, the coefficients before the sine function, I might as well just highlight the sine function, right? The things that's multiplied to the sine function, it should be the same for top and the bottom, right? The top row and the bottom row. Same thing, the expressions multiplied to the cosine should be the same for top and bottom. What that means here is I have k times cosine of phi, that's supposed to equal to a. In other words, a is equal to k times cosine of phi. Similarly, I have sine of phi, but don't forget again that k gets distributed, that's supposed to equal to b. So I have b equal to k times sine of phi. What I can do here is to simplify or rewrite the expression a little bit. I want to solve for cosine of phi for the top. So I just divide k on both sides. I get a over k equals to cosine of phi. On the other hand, dividing k on both sides gave me b over k equals to sine of phi. So why does that help? Well, because we know the expression for cosine of phi, sine of phi, this thing right here, as a terminal point corresponding to the angle phi. In other words, the coordinate point of a over k comma b over k, that coordinate point is the terminal point of the terminal point corresponding to the angle phi. This is going to help me identify exactly what this phi value is going to be. And then on top of that, we also recognize this k is really the distance from the origin to the point A and B. Therefore, by the distance formula, we got k equals to square root of a squared plus b squared. So the formula I need to find the k value and the phi value here is really developed in the process. Okay. So let's go ahead and see this in action. The first step is the same, but turns out the first step in finding the k, that is, right? This step is the same, you should always start with this. Really not much uh, not much argument there. But then to find this phi, you actually have two different methods. Two different methods depending on what your given is, and honestly depending on what class you're working for. So let's take a look at these two methods. Well, the first step is to find k by using the formula. That part we know. Let's go ahead and just highlight that and use it. So this is the first step. The second step, again, is where it is going to be different depending on the class what are given. If you're given random numbers for a and b, very likely these are going to be calculator solutions. Okay, these are calculator solutions. So the most straightforward way of thinking is to just definitely do tangent, right? Because cosine is for the cosine is for the x coordinate, the first coordinate. Sine is for the second coordinate. So I guess for tangent is the easiest one to use because then you get second coordinate over the first coordinate, which actually come out to be b over a. But there's a small issue here because of the range of tangent inverse is negative 90 degree to 90 degree. You actually have to change up the formula a little bit depending on the quadrant that you're working on. So this method number one, rely on the formula theta, or phi rather, is equal to tangent of b over a. Tangent inverse, sorry, of b over a. But because of the restriction or the range of tangent inverse, we actually have to work a little bit more to identify which quadrant we're working on. If we are going to see that a comma b is in quadrant 2 or quadrant 3, we actually have to use this formula instead. Okay, so we have to add 180 degrees. Okay, so basically you have to identify the quadrants before you can use the formula, choose the correct formula. All right, so let's see a quick example. The wording here is rewrite this expression into an expression involving sine only, and this is the version of the question that the book used, and of course this is the one that I'd be using. So the solution here is fairly simple. Let's go ahead and calculate our k first. K value is equal to square root of a squared plus b squared, right? So the a is the coefficient of sine, b is the coefficient for cosine. Actually, let me just write this down here. Okay, so it's going to be negative 3 squared plus 5 squared, and that's going to come out to be negative 3 squared is 9 plus 5 squared is 25. 9 plus 25 is 34. Okay, so this one is not too bad to do. And then I need to look at the quadrant for a comma b. Well, a comma b looks like negative 3 comma 5, and this is going to be in quadrant 2. Right, because for quadrant 2, the x value is negative, the y value is positive. Because this is in quadrant 2, I actually have to use this formula instead. So my phi here is equal to tangent inverse of b over a. Again, b is 5, a is negative 3, but then I have to plus 180 degrees. Now, most of the time when you're working on this problem, you will need uh, the degree notation, uh, the degree measurement. You can use radian, of course, but for the majority of these purposes, you will be using degree. So make sure your calculator is in the right mode. Otherwise, you're not going to have a good time, right? So tangent inverse 5 over -3 plus 180 degree. Let's go ahead and punch that in. 5 over -3. And then, by the way, if I just stop here and press enter, this is the answer I will be getting, right? Is -59 degree. But remember, this is because the range of the tangent inverse is from -90 degrees to +90 degrees. This is exactly why we need to add 180 degree, and this is my answer, 120.9637, right? Depending on whichever digit you ask to round to. Let's do 120.963, 964. 964 degree. Okay, and we should double check, right? 120 degree is definitely somewhere in quadrant 2, so I know I'm probably doing this right. Okay, and finally, at the end of everything, we write our answer in terms of sign. It's always going to be this expression, k sine of x plus phi. So the final answer is k, which is radical 34, sine of x, probably need more, a little bit more room here. Sine of x plus 120.9, I'll just put 96, I'm running out of room here, degree. Okay. And that right there is our final answer. So k sine of x plus phi. Okay, so this method is easier in the sense that you just have to rely on the calculator. Your biggest task is to make sure you're using the right formula. Okay, it's not too bad to do here, but is something that you have to be a little bit careful in terms of identifying which formula you're supposed to use. Let's do the other version of the problem, the other method. The other method, which is the method we are often time going to use in this class, because it is a math class after all, we're working with radian, and you probably already realize this, but whenever we're working with radian, we are working with, we want exact answers, and we want to do this without really using calculator. Again, you can use this in terms of degrees if you do the modification of what I want to show you next, but most of the time we are working with radian. Now, these problems have to be given to you in a specific way. Because we're relying on the unit circle, we can't just randomly give you numbers and then hoping that it will work out, because, well, very likely it will not work out. So the given here has to be more exact. It can't just be random two numbers, like how we did in example 6. In some sense, though, this makes the problem a little bit easier to do. But let's take a look. So we identify our A and B because, again, we want to solve for K first. Here's my A, and for B, I do need to include that negative sign as well. Okay, so here the K is equal to square root of A squared, so is 2 radical 3 squared plus b squared, which is negative 2 squared, 2 radical 3 squared. The 2 squared is 4 times the radical 3 squared is the positive 3 without the radical, plus negative 2 squared. Again, that's just 4. So it comes out to be square root of 4 times 3 is 12 plus 4, which is 16. Square root of 16 is just 4. Okay, so your k value come out rather nicely, and this is probably the one time, or one of the few times, if there's more, where I'm going to ask you to simplify your radical if it comes out to have a radical. Most of the time, you will come out to not have a radical. You just have nice answers, just like what we have here. But if you do have a radical, unfortunately, you have to simplify a little bit. Okay. But once this is done, the next step is simpler compared to the previous method, because all we have to do is to find phi that is corresponding to the coordinate a over k comma b over k, which in this case is going to be 2 radical 3 over 4 comma negative 2 over 4. And you can already see where I'm going with this, hopefully. Once you cancel the 2 and the 4 on top and bottom, you're going to have radical 3 over 2 comma negative 1 half. And this is a very familiar coordinate that we know to be on the unit circle, right? And for this method, it's always going to come back to the unit circle, so it's always going to play out this way. And from here, all we have to do is find out the corresponding phi, which in this case, because this coordinate here is in quadrant 4, this is going to be 11 pi over 6. Okay, because everything in quadrant 4 follows this pattern, which the numerator is, 1 less than twice of the denominator. So we find our phi, which is, a lot simpler than before in my opinion. So the final answer here is just going to be 4 sine of x plus 11 pi over 6. Okay, so it's a lot more clean than the previous method, but as always, is less universal because we're restricted on the unit circle. The idea for this method is that the original expression here for a and b, this is a coordinate potentially outside of unit circle, but it's still on some circle. When we find the distance and we divide it by the distance, is to bring this bigger circle, right? If we divide it by the radius of the circle, then we, bring it back to a unit circle, which is why our answer is always going to be a familiar angle on the unit circle. Okay. So this is the two method. You should know both of these for application purposes. For this one, really the method 2 here, this is used quite a bit in your engineering classes and your physics class. But for math classes, we're going to use this method. And we are going to see this method again in the later side of the class, which is the last portion of the class in chapter 5. Okay, so definitely review this one. This one is important for us, even though it's more restrictive. Okay, so that's it for me for this class. We really gone through a decent amount. You can see it's a little heavy. This is why it might be a good idea to review these material, uh, once in a while, so you're always familiar with the idea. Okay, so that's it for this video. I will see you guys in the next video.